Chapter 1, I think this is video 4, doesn't matter, resonance structures. And resonance structures are extremely important because the more structures you can draw for a given compound or ion, the more stable it is. Some compounds and structures are not adequately represented by a single Lewis dot. And that's what we're going to find out, and most of these are going to be ions format. In other words, there may be two or more possible structures or rearrangement or possible arrangement of the electrons. We're not going to move any atoms or nuclei. We're only going to move electrons. A hint when moving electrons, I will always circle them usually and then draw the arrow to where they are going. There's a general rule: if I draw a double arrow, they're both going. If I draw a single arrow, only one is going. That is the common language of organic chemistry. We use the double arrow between the structures to represent resonance. Don't confuse it with equilibrium. Equilibrium was arrow going one direction, arrow going the opposite. When they're double, that's the equilibrium. So let's get started. So if I have this ion, and I'm going to use colors to represent, this carbon is electron deficient. The nitrogen is electron rich. So these pair of electrons can form a bond. So now our resonance structure, you see, and a double bond nitrogen. And now the nitrogen has a plus charge. Now with most of these, there always has what is known as a minor and a major contributor. We're mainly interested in the major. In this case, this is our major contributor. The reason it is because carbon here has 8 electrons around it, and so does nitrogen. Where if we go over here to this molecule, this carbon only had 6 electrons around it. Nitrogen still had 8. So this is our major contributor. This is the most likely structure. But both of them work together. So if I have, too far, Bob. If I have this ion here, it's the acetate ion to be exact. I have this oxygen here marked as like radioactive. It's a marker for tracing purposes. So what can happen here? Electron pair here can form a double bond. Then I realized I didn't put my electrons around this one here. It has 2 pair. And when that's happening, now carbon has too many bonds to it. So one of the pi bonds breaks. And now our resonance structure And I need to put my tracer on here because we want to trace that all the way through. As an example, sometimes then, since this oscillates back and forth, you may see it drawn this way. In this manner, with just a negative charge here, as it oscillates back and forth. So these are resonance structures. So if I have methyl nitromethane, the same thing is going to apply. This nitrogen, though, right now has a positive charge on it because it doesn't have a pair of electrons. So the electrons can form a double bond here. When that happens, when the pi electrons from the C double bond O break. And this is going to be negative charge. This nitrogen we said is positive. Here again, it is able to oscillate back and forth. Kind of cool. Remember, we're not moving atoms. We're moving only the electrons. That's all we're interested in. So here I have one. This is already the major. Contributor. So what can happen? Oh, and I got too many electrons on the oxygen. Not smart, Bob. There we go. I can delete them very easily. So, one of the minors, remember, oxygen is highly electronegative. It can attract the oxygen, the electrons from the carbon. So its resonance structure is going to be negative. And since that is negative, the carbon is going to be positive. But hopefully we know that this one here is the major because everything has the octet rule. So let's look at this molecule. This is a type of ether. We're missing a proton over here, so this carbon has a positive charge. So what could happen? This carbon is short electrons. It wants to have 8. Pair of electrons here from the oxygen can form a pi bond, a double bond. Since this oxygen now has 3 bonds, it's going to be positive. So let's evaluate and see which one of these two is going to be the major contributor. What we do is just have to start counting electrons. We didn't mess with this carbon. This oxygen has 8 electrons around it. Double or single bond is 2, another single bond is 4, 6, 8. This carbon has 6 electrons around it. It wants to have 8. So if we go over here, this oxygen has 8 electrons around it. This carbon here also has now 8 electrons around it. So it is the major contributor to resonance. So now I have another one. And I notice I got too many oxygen electrons on my oxygen. That's okay. So there is the correct structure. Right now, everything has 8 around it. I have an electron pair here. So, up this pair of electrons can form a double bond. But now this carbon here has too many electrons, so the pi bond will take a pair of electrons and transfer them to the oxygen. The question is, which one of these is going to be the major contributor? Because everything here already has 8 around it. And in fact, the major contributor is the structure that we just put up, because oxygen is highly electronegative. It can take on those electrons. Kind of cool. Still remember, we're only moving electrons. So here I have another one. Let's see. Right now this is 8, 8, and 8, so we're good. A pair of electrons here could form a triple bond. But now this nitrogen has too many electrons. So these electrons can just go to the carbon. And by the way, this nitrogen is going to be positive. And it is positive here also. So which is our major? Well, this one has 2 charges, where this one only has 1. This one is our major. This one is our minor. Oh yeah, this is a good one. This is a good one. Give you a little bit of time to draw this structure. Has 5 carbon, 2 double bonds, an OH and an NH2. Now we're going to take a little bit of time on this one, I can already tell. So electron pair here could form a double bond. I may try to straighten this out. That carbon's going to be positive now. Keep my electrons. So far, so good. I'm going to scroll down here a little bit. So now, too long a line. We can have another resonance structure. In fact, there's two possibilities off of this one here. We can move a pair of electrons from the oxygen to form the double bond. Now that oxygen is going to be positive charged. So that's another resonance structure. There is also another one off of this same structure because of the double bond. So what could happen? Let me erase a little bit here. If this doesn't occur, oops. The other possibility is this pi bond here. Can break and make a pi bond with the carbocation, the positive charged species. So now we have CH2 I lost my hydrogen here, that's okay. I have a tendency to lose hydrogen. Yeah, I lost a lot of hydrogen. Should have been a hydrogen there also. If you notice, hydrogen really don't matter. But here now we have another positive charge. It has moved to the other side. And then there's one more. This pair of electrons from the nitrogen can form a double bond. So now I have my CH2 bonded to a CH, bonded to a C, double bond CH. OH is still here, bonded to a CH, double bonded to a nitrogen, and it has a positive charge. And all these are resonance structures. And the more resonance structures that you can draw, it increases the stability of the molecule, which is a good thing. This one was the one that you had to realize there was two possible structures coming off of it. A pair of electrons from the oxygen or the double bond pi bond Moving over. If you notice, the electrons never jump. Well, they always happen to the atom right next to them, or form a bond right next to them. They never jump across the molecule. They cannot do that. So, if we go back now and count, this carbon here only had 6 electrons around it. Not good. This carbon here had 6 electrons. Here, everything here, well, I'm supposed to have my hydrogen. Everything here has 8. That's fine. That is somewhat of a major contributor. When we go here a little bit further, this one here has 6. But when we get to this one here, everything has 8. It is also a major contributor. And those increase the stability or likelihood of the molecule. So resonance structures, when we start moving them around, the better it is. The more likely the structure, it increases the stability. We're always looking for major products or major contributors to that resonance structures. Kind of deep. We're going to do lots of resonance structures in organic chemistry. Organic chemistry basically is you're an accountant, like an accounting class, but you're an accountant for electrons. All we're really interested in is the electrons and accounting for them.